Hi everyone, hope you're all well. My name is Miss Holloway and I'm one of the maths teachers here at Ashton Park School. And I just wanted to give you a very quick overview about what it would be like to study A-level maths at Ashton Park and go through a few examples of what we do during lessons when we are studying maths A-level. So some of you might already be aware that Maths A-level is divided up into two overall sections. First of all, you have the pure maths, which is much more based in theory and will include a lot of algebra, so things like index laws, things you've come across before, trigonometry, and then it also will go into things that will be new in A-level. The most notable new thing at A-level is differentiation and integration. You might have come across that before a bit, particularly if you've done the additional maths course, but it involves manipulating algebraic expressions so we can understand what's going on, particularly with gradient and area under curves, which we can use for modelling purposes. Then we also have an applied section, which is split into two. We have statistics, which is something that, even though it goes into a lot more detail, you will be familiar with from your GCSE. And then the other applied section is mechanics, which is what I thought I'd go through with you a little bit today, because it's probably the least similar to anything that you would normally be doing in during your GCSE courses, even though it does use a lot of the same underlying concepts. So we, first of all, when we're thinking about mechanics, we think about forces. So immediately you can probably notice that there are a lot of parallels between the mechanics side of maths A-level and physics, and some of you might be doing physics as well as maths because they are very compatible subjects, and there is some overlap here. Okay, so for example, when we're thinking about forces, one of the ways that we start thinking about it is if I have an object on a surface and I wanted it to move, what kind of forces does that object encounter? So first of all, you've got the weight of that object pressing down on the table, which we're all aware of our own weight. Then if you try to pull the object along the surface, in this case a table, the surface will probably not be completely smooth. There will be friction, which if you try to pull the object along, you'll be able to feel some resistance, you'll be able to feel the friction. There's also a force acting on the object from the string. So if you pull the string, there will be tension generated in the string, which will cause a force to act on the object. And if that tension force is strong enough, it will overcome the friction and the object will start to move. There's also one final force that we call the reaction force. So if, as I was saying, like we're all aware of our own weight, you might be sitting in a chair at the moment, you might be standing, but either way, you can consciously notice the feeling that you have of your weight pressing down into the chair or into the floor. But what you don't normally think about is that the chair or the floor is also creating a force on you, which is equal and opposite to your weight. And the reason we know that the force must be there is because you are not currently sinking through your chair or through the floor. So in order to stop that sinking happening, there needs to be an equal and opposite force to counteract your weight. Now we're going to talk a bit about vectors in a second. I'll skip through that a little bit. But this is again where it comes back to physics. So you may have come across this formula already, and it is actually used in maths GCSE as well, that force is equal to mass times acceleration. So once we've started considering forces, we can then start considering the motion of an object. Now, those two graphs, displacement time graphs and velocity time graphs, again, this is something you will have covered at GCSE. So initially, it's not a brand new concept, but again, we'll go through it in a lot more detail during the A-level course and see how we can bring more details into a model to make them more realistic and more accurate. And a lot of mechanics, when we're thinking about motion, we use what we call SUVAT equations, because SUVAT uses the acronyms, the initial letters that we use to represent things that are involved in motion. So the A and the T, they're pretty obvious what they stand for, acceleration and time. We also consider two velocity values when we're thinking about motion. We think about the initial velocity just before an object starts moving, or maybe it might have already started moving by the time you start the timer. And the final velocity, how fast is it moving at the end of whatever time period you're looking at. Then we also use S for displacement, which is probably the least intuitive. But it's because if we use a D, we wouldn't necessarily know if we meant distance or displacement. S is very clearly displacement. So one other thing that we have to consider when we are using mechanics modelling is that we might be considering a real life situation with a real life object. But in order to model it in maths, we make some assumptions that make the model simpler, which make it a lot easier to analyse. So one of the basic assumptions we make when we're modelling in mechanics is whatever object it is that we're thinking of, we model it as a particle. And what that means is we don't necessarily consider the shape of the object, and it means that the mass is all concentrated at one point. So in real life, you might have a box, for example, that maybe is heavier at one end than the other end, depending on what's in the box. But for modelling purposes at A-level, we assume that that box is just one single point where all of the mass of that box is concentrated at one point. If you continue mechanics, possibly doing physics or engineering or something like that past A-level, then we will consider that a lot more complex things going on. But at A-level, we only need to worry about the simple modelling. We also consider whether or not the surface is rough or smooth, and that would depend on whether or not there's any friction. We also sometimes consider pulleys. So again, we might imagine that there's a real life application of considering pulleys in when we're thinking about machinery in a factory, needing to raise a heavy weight. Is there a way that we can do that by using the least amount of force possible, and therefore the least amount of energy? And we model strings as being inextensible, so there's no stretch in the string. They can't get longer if you pull on them. And then we also will sometimes consider a rod. So sometimes a particle isn't a meaningful enough model if we want to model something as being having its mass distributed along, for example, like a stick. That could be modeling like a plank or a steel bar or something like that. And we have supports as well. We also use standard units, which again are things that you will come across in physics as well, which are all ones that should be familiar to you. The only one that might not be completely familiar here is newtons, which is the it's a sort of shorthand way of writing kilograms per meter squared, and it's a unit of force. Okay, so another thing that we think about in mechanics, and again, this is something you will have come across at GCSE, is the difference between a vector value and a scalar value. So a scalar quantity, as it says there, only has magnitude. If I asked you to walk for 5 meters, you could choose whichever direction you want to walk in. However, if I wanted to be very specific and give you a direction as well as a distance to walk, I would give you a vector. Okay, so in this particular vector, that's a column vector. Again, that's something you've come across at GCSE, meaning that from where you start from, you move 3 meters horizontally and 4 meters vertically, and overall that will give you a diagonal distance of 5 meters because it would be a right angle triangle. And using Pythagoras, if the two shorter sides of the triangle are 3 and 4 meters, the longest side must be 5 meters. So lots of different measurements have scalar forms and vector forms. So like we were just discussing distance there. Speed is also scalar. Speed doesn't give you the direction that you're traveling in. So why don't you pause the video now and see if you can think about what might be underneath the green boxes, and then press play when you're ready to carry on. Okay, so we've already mentioned velocity. So velocity is speed with a direction. So speed is a scalar. It just tells you a value, whereas velocity also will tell you a direction as well as the speed that you're going at. And the vector form of distance is displacement as well. We've mentioned that. Most other quantities can be vectors or scalars, such as force and acceleration, so that they can have direction as well as magnitude. But there are some things, such as time and mass, that can only be scalars because, for example, we have no control over what direction time goes in, so we can only use it to measure the amount of time that passes, not the direction in which time is traveling in. So I am going to also get you to think about your GCSE maths knowledge to try to answer these questions. So what we're doing here is we're moving between scalar form and vector form for various different vectors, if you like. So the first one, you've got the magnitude of that vector, the size of it is 5 meters, and it's moving at an angle of 60 degrees from the horizontal. So you can use trigonometry to work out the horizontal component of that vector and the vertical component of that vector. And that's really a really important skill that we use in mechanics a lot, is separating a diagonal vector, whether it's a force or a displacement or anything like that. We often separate it into a horizontal and vertical component because that makes it easier to manipulate and to analyze, especially when we've got more than one vector going on. But we can also go back the other way, like the middle example. You've got your column vector. So you can imagine there drawing a triangle where you're going along 5 and down 12. Again, you can use Pythagoras this time to work out the diagonal between them. So pause the video, see if you can figure out what's going on underneath the green boxes, and then press play when you're ready for me to move on. Okay, so again, using trigonometry, we can work out the horizontal and vertical components of this force. So you get 2.5 over 4.33. And then we can use Pythagoras to work out the diagonal component of this force here. So if you have 5 squared plus negative 12 squared and square root the answer, you get 3. And then that last one there, again, we can use trigonometry to work out the horizontal and vertical components of this force. So there's another 3 questions for you to have a go at on this slide. So you can pause the video again and see if you can use what we talked about on the previous slide to answer them. The only difference here is that for the middle question, instead of using the column vectors to represent the vector, we're using this new notation that you might not have seen before at GCSE, where we use I and J. We call it IJ notation. So the I component is the horizontal component and the J component is the vertical component. So it's just another way of writing a column vector 6, -8, as it says in the box. So again, you might want to pause the video, have a go and see if you can figure out the missing values, and then press play when you're ready to move on. Okay, so using trigonometry for that first triangle, we can work out the horizontal and vertical components, and we can simplify that to -3√3 for the horizontal component and -3 for the vertical component. And the reason they're both negative is because the direction of the vector is going down and to the left diagonally, which means that our horizontal component needs to be moving left and the vertical component needs to be moving down. Then again, I can use Pythagoras for the second one to work out the magnitude of the vector, and I can use trigonometry for the last one as well. Okay, and we've written it there in IJ notation instead of the column vectors. Okay, so why don't you think about what we've just been talking about for the last couple of slides, pause the video, see if you can figure out the answers to these questions, then press play when you're ready to move on. Okay, so first of all, it's always a good idea if the question hasn't given you a diagram, and this is true, I'm sure, in GCSE as well, that drawing a diagram is always really helpful. So to think about how to get from A to C directly, again, this is GCSE knowledge. We can add together the vectors AB and BC to get 11i minus 8j, or 11 negative 8 if you use the column vector. And then to work out the distance, the magnitude of his displacement, which is the distance, we can use Pythagoras to work out that it's 13.6 kilometers. And then the total distance, we need to work out the magnitude of all three of these vectors. We've already done AC. So we need to work out the magnitude of AB and BC and add them together. So you can see that by walking for the two other vectors, he's walked just over 7 kilometers, or just under 7 kilometers, sorry, more than if he'd walked there directly. And then we can answer the looking question as well. If you had a go at that, it's 18.4 degrees. Okay, so there's just a couple of things that I just wanted to show you of how we can apply all of this vector mechanics knowledge when we are thinking about modeling real life situations. So one of the things that we think about is projectiles, which often comes up in GCSE questions as throwing a ball or an object and thinking about where's it going to come down. The applications of that in real life, one of them might be military applications, but then you've also got the idea of launching things into space, because when you launch things into space, you want to make sure that it doesn't come down again. So you need to figure out what velocity you need to launch your rocket at so that it manages to keep going until it breaks out through the atmosphere and doesn't end up being overcome by gravity and coming back down to Earth again. And one of the things that helps us think about that is thinking about the highest point. So if you think about velocity having direction as well as a value, as well as a magnitude, when you launch something into the air, initially it will start going up, and then at some point it starts coming down. So there's like a fractional moment at the top of its trajectory where it's neither going up nor down, just as it's changing from going up to going down. And at that point, the velocity is 0 because it's not traveling up or down. The vertical velocity is 0. So that's why it's useful to break forces down into their vertical and horizontal components, so you can think about the vertex of a trajectory there. We can also think about friction. So why don't you pause the video for a second, think about what might be under the green boxes, and then press play when you're ready to move on. So in the first example, there's no friction, okay? There is the weight of the object and a reaction force to stop it falling through the surface, but it's not moving, and so friction won't act on an object unless it's moving. In the second scenario, we can say that the tension in the string is either exactly equal to or less than the frictional force, because it's not strong enough to overcome the frictional force, which means the object doesn't move. And then in the last one, it means that the tension in the string is much bigger, and therefore it's overcoming the friction. So even though there is still friction on the surface, because the tension in the string is much bigger, it means that the object will start to move. And then the last thing I just wanted to talk about is something that, again, you've probably never even considered this, even though it impacts your life every day, is why are door handles on the opposite side of doors to the hinges? So why don't you pause the video, have a little think about why that might be, and then press play, and I'll talk about how that applies to mechanics. So the reason the door handle's on the other side is because the further away from the hinge the handle is, the easier it is to push the door open. And if you think about trying to push a door open, if you put your hand on the door right next to the hinges, it will take a lot more effort to open the door than if you put your hand on the other side of the door. And the reason for that is to do with what we call moments, okay, which, oh, that's not coming out in the right, there we go. So the moment of a force measures the turning effect of the force on the body on which it's acting, okay, and we have got this equation in mechanics so that we can tell that the moment of a force is equal to the force times the distance from the point about which it's rotating. So and it has to be a perpendicular distance. So if you have a look at this example here, you've got a rod that's being balanced on a fixed point there at A. You've got more than half of the rod on the left-hand side and less than half of it on the right-hand side. And you've also got these forces acting on the rod. Maybe you've got a weight, someone sitting on each end of the rod. The force that's acting on the left-hand side is 700 newtons vertically downwards. On the right-hand side, we weren't initially given the force, we were given the mass of the object. But again, we have to remember that mass is not a force in itself. We need to work out the weight, which is mass times acceleration. And in mechanics, we use gravity. Again, you think of gravity as being a force that just pulls you down, but actually gravity is best modeled as an acceleration. So that a 75 kilogram mass on Earth will give about 750 newtons of force, because gravity is about, very roughly, about 10 meters per second or meters per second squared. So that we can tell that the moment on the left-hand side is about 7,000 Newton meters, and on the right-hand side it's 5,880, which would mean that the rod would tilt in an anti-clockwise direction because there's a greater force on the left-hand side. So last thing, why don't you pause the video, see if you can use the equation of, I'll just put it there again, that the moment is force times distance. See if you can figure out what's under the green boxes. Press play when you're ready for the answers. Okay, so we're just multiplying the force by the distance. For the second one, there is no moment because there's no turning effect, because the force is pulling directly away from the object. And then in the rest of them, we have to see that the distance that's given in the diagram is not perpendicular to the force. So we first need to use trigonometry to work out the perpendicular distance before we can multiply it by the force. Okay, so that's it from me. I hope you found that interesting. And I'm looking forward to meeting you all when we start the A-level course next year in Ashton Park. Thank you very much.